All right, guys. So I got this. Well, first of all, I hope everyone's doing all right. Hope you guys are healthy and you're doing social distancing and all that good stuff, practicing good hygiene. Also, I hope you're exercising a little bit, getting some, physical activity, not just sitting around. But anyways, so this video is to give you the answers to the book work. I left my teacher copy of this book at school. So I'm going to just do this out loud. I sat down to type the answers out yesterday and it was taking too long. So this is how I'm going to do it. I got to figure out how to get my teacher copy, which would be a lot easier, so I can just record a video and show you the answers in the book, and then you can pause the video if you want. To check your answers. So I'm just going to go over it like it was class. I'll go through each one as quick as I can because there's a lot and I don't want this to be long. I don't really know where to go from here. I don't know how often I'm going to do videos, but I'll try and give you work every couple days to keep you, learning some new stuff here. Yeah, I got this contraption set up. I'm actually in a finished room in my basement. Kind of hard to explain, but I got an iPad up here recording this, and I actually have a Surface Pro over here that I will put down here, and I can write on it with a stylus like a whiteboard. So that's how I'll do notes or explain things. Like the homework due today, or the work due today, I will later today or tomorrow go through how to do that on that. So this is kind of how I'm going to do it, I think, as far as any sort of video. I know there's no back and forth. But anyways, so here we are. Hope you guys are doing well. I do miss class, miss school. All right, here's the answers. So let's see. The first one here, 414. 14, what determines a substance's state at a given temperature? The strength of the forces of attraction. If the forces of attraction are really weak, it's a gas. If the forces are really strong, it's a solid. Somewhere in the middle, it's a liquid. But liquids are much stronger than gases. And again, forces meaning if you have two molecules, they are attracted to each other. And the closer they are together, the more it's like a solid, which means stronger forces. Further apart, like a gas. 15, compare and contrast. Intermolecular and intra are both forces that hold atoms or molecules together, but the difference is inter is between two molecules, whereas intra is like a bond between atoms. You know what? I can actually, let me do this right now real quick. Let's see here. So let me make sure this is working. Yeah, all right. Let me clear that. All right, I wonder if I can zoom in here. All right, so basically inter, so if you have water molecule here, so right there is intramolecular, that's a covalent bond, and then ... a hydrogen bond to another water molecule, that's your intermolecular. So inter are way weaker than intra. When you boil, melt, phase change, this is what's broken or formed. This is chemical reactions. Chemical reactions break that. So intra is like a bond, covalent bond, polar bond. This is a force of attraction. Intermolecular, dispersion, hydrogen bonding, all the stuff we just are talking about. Okay. 16, which can form hydrogen bonds and dispersion. H2, dispersion, because it is a non-polar molecule. HF, hydrogen bond, because it has H with NO or F. Kind of like here, that's a hydrogen bond, so HF to HF would look like this. So there's your partial negative, partial positive. But because it's hydrogen with F, that's a hydrogen bond. Okay. In methane, there are 4 single All right, so methane's a gas, octane's a liquid, and the reason for that is because there are more bonds, there are more electrons. There's 2 electrons per bond. So since there's 4 single bonds, that's going to be 8 electrons, and then 2 times 25 is 50 electrons. So more electrons here mean stronger dispersion forces. So if it has stronger dispersion, it has a higher melting boiling point. Therefore, at room temperature, this is a liquid with stronger forces. Weaker forces, it's a gas. All right. Hold on a second here. I got to go back. Give me a second. Here we go. All right, 434. And you know what? Maybe, let's see. How long is this? All right. I don't want the videos to go too long. So, let me see. Why is it doing that? There we go. Oh, you guys couldn't see that one, could you? Let's see. This is my trial run here. Oh yeah, you can't see that at all. My contraption here is not working out the way I wanted it to. Hold on. Give me a second. I had it all set. Here we go. Oh, you know why? Because I zoomed in. There we go. I forgot I did that. There we go. All right. So anyways, there's that. Let's move on. I just went over those. Hopefully you followed me on that. All right, 434. All right, 51 through 55. 51, temporary dipole and permanent. Temporary is one that doesn't last very long because electrons are moving around, and permanent is one that is always there. And if we look at this here, let me erase this really quick. So for example, if you have methane molecule, CH4, and it's attracted to another methane, what happens is electrons are moving around because it's nonpolar. It uses dispersion, and what it happens is it forms a temporary negative, temporarily positive, let's say, and that allows these to be attracted, but that breaks very quickly, and then the molecules move around because it's a gas. So that's temporary. So that's not always going to be there. It's a little more complicated, but given the situation and time, I'm going to leave it at that. If you take something like HCl, because of that dipole, 2 HCl are attracted with permanent dipoles. That's permanent because these are polar molecules. So Cl is always winning that tug of war. Here, because these are non-polar, there isn't really anyone winning. There's no dipole moment. There's no permanent partial charges. So this is permanent dipole, temporary. Okay, what's next? Why are dispersion forces weaker than dipole? I just explained that. Dispersion uses those temporary dipole. Dipole uses permanent. So permanent are much stronger than temporary. Why hydrogen bonds are stronger than most dipole forces? Because H with N, O, or F. So when hydrogen bonding forms between a molecule with hydrogen and then a molecule with nitrogen, oxygen, and fluorine, these three have really high electronegativities. So they form those dipoles much better. The poles are more opposite, we'll say, because they have really high electronegativity. So for example, HF would be attracted to another HF using a hydrogen bond, and that is stronger than this one here because it's a special type of dipole called a hydrogen bond. So those partial negative, partial positives are stronger. All right, what's next? 54, we already did that. Intra and inter. Why longer nonpolar redact? All right, so 55 is just like that one question over here. with methane and octane. The bigger the molecule, the more electrons, more temporary dipoles, stronger forces. So more electrons, stronger dispersion forces. That's kind of the gist of that. All right, what's next? 58, 59. Which can form hydrogen bonds? 58. Let's see. So H2O can do it, and H2O2, and actually, they all can. They can all do hydrogen bonds. Hydrogen peroxide, H2O2, doesn't do it very well because it's actually a non-polar molecule with the way that it's shaped, sort of. Not really. It's a little more complex because of the geometry of it, but for sure on the regents, water, HF, and ammonia, they all have H with N or F or O. 59 here. Decide which can form intermediate and then draw it. Show several molecules attached to it. All right, so here we go. All right, let me erase these here. So the only one that can do it is H2O2, and H2O2 looks like this. So this oxygen here, let's say, could be intermolecularly attracted to an H on another hydrogen peroxide molecule. So there's your hydrogen bond there. There's your H bond. So that would be an example. The O from one molecule, the H of another, in between, intermolecular, that's your hydrogen bond. So that would be number 59. All right, let's see. 436, number 84 and 88. 84. Use intermolecular force to explain why oxygen is room temperature. All right, so oxygen's a gas because it has weaker intermolecular forces. Particles are more spread out. Water is a liquid because it has stronger intermolecular forces. The particles are closer together. Specifically, it uses hydrogen bonds, which is the strongest force of attraction. 88. 3 types of forces. London dispersion, dipole-dipole interaction, hydrogen bonding. Those are the 3 common. You could also put ion dipole in there as well. 439, number 10. Let's see. Bond strength and bond length. All right. So look at this. We got 435. Wait, you know what? I feel like I'm going to zoom in on this one a little bit here. All right, so what do we got? Okay, so summarize the relationship between bond strength and bond length. So bond strength, 435, and the length is 74. Next smallest number there. So that looks like the biggest number. The next one from there would be 393 and 104. So I'm seeing the strength going down, the bond length going up. Let's see, 356. So that's a little bit weaker, a little bit longer. After 356, 347, that's a little bit longer. And then let's look at the weakest one. The weakest one here would be 151, and that's the biggest. Yeah, so the answer to 10, summarize the relationship between bond strength and bond length. I would say it's an indirect relationship. As bond strength decreases, bond length increases, which makes sense because if we have, let's take the example, if we have H bonded to H, okay, and let's say the distance is from here to here, right? So that's 435. That's the strongest one. And then the weakest one is I, and that's the longest. So if we had I bonded to I, let's say that's the, right? So from here to here, that's a short or a longer distance. So it would be easier to break that. Here to here, shorter distance, harder to break that. And the reason for that, if you remember bonding, is you have the positive nucleus, and then you have the electrons around it. Well, this nucleus is attracted to that electron, this nucleus is attracted to that, and it sucks them close together. So if that attraction is stronger, they're going to get pulled closer together. If that attraction is weaker, they're not going to be pulled as close together. That's why this makes sense. The stronger it is, the harder it is to break. That means the closer it is together, the shorter the bond. Okay, next. 232. Let's go back. 232. Let me zoom out again. I keep forgetting about that. 232. Let's see. 60 and 63. 60. What does the term electrically neutral mean when discussing ionic compounds? That means the cation and anion add up to 0. So for example, just take salt really quick, Na plus 1, Cl minus 1, they add up to 0. Take another example, magnesium, chloride, MgCl2. If each Cl is -1, that's a -2, Mg is +2, so that's adding up to 0. That's what it means by electrically neutral. The next one is what? 61, 62, 63. All right. Discuss the formation of ionic bond. It's when a metal loses electrons, forms a cation. Oops. What did I just do? Hold on. Sorry. Stay with me. So metal, so Na, for example, gives 1 electron to Cl. So Na loses an electron, forms a positive one. Cl gains is negative. They both get a full octet, things we've already discussed. They come together, they're attracted, they make an ionic bond. So the cation and anion are attracted. How'd that happen? The metal gave an electron to the non-metal. Okay. Explain why potassium does not bond with neon to form a compound. Neon already has a complete valence shell, so it has no reason to form any bonds. Or has a complete octet, it's another way to say it. 63, physical properties of ionic linked to ionic bond. They conduct electricity when dissolved in water or when they're a liquid. So if you melt it, it still conducts because the ions are mobile. Ionic solids have high melting points. You could also say high boiling points because that could count as a third. They tend to be fairly dense because the bonds are strong, keeping the ions close together. They have low vapor pressure, meaning they're not going to evaporate. If I pour salt on the table, it's going to sit there for like ever, basically. It's never going to evaporate. Why? Because it has really strong bonds and forces holding it together. Okay, there's your properties. I'm trying to go quick here, guys. Sorry. 63, 233, 81. Oh yeah, okay, 81. See this, if I had the teacher copy, I could just show you the answers. So, but I'll do this quick. 81 BCE, 82 BCE. All right, here we go. All right, here we go. Make sure you can still see this. Okay, 81B, silver 1 bromide. That means Ag plus 1, Br minus 1. So it's just AgBr because that adds up to 0. These copper 2 chloride. Copper 2 means Cu plus 2. Chloride is minus 1. Use that top negative charge. I need 2 of these, CuCl2, to balance it out to 0. So that's B, that's C, and then E, silver 1 acetate. Can I fit that in the bottom? Yeah. So silver 1, Ag plus 1. Acetate, C2H3O2 minus 1. That's on reference table E. So that's the acetate ion. Since it's plus 1 and minus 1, I don't need subscripts, so it's just AgC2H3O2. That's kind of a tough one. All right, 82, again, B, C, and E. B, CaCl2 is calcium. Oops. And then Cl is chloride. So just calcium chloride. Magnesium for the next one. Magnesium nitride, because that's Mg3N2 for number 82. And then E is potassium. And NO3 is on table E called nitrate. Potassium nitrate. Okay, so that's B, C, and E there. All right. Next. Oops. All right. Home stretch. 87, 89. Describe a metallic bond. It's a sea of electrons that are surrounding fixed metal cations. Okay. And 89. How malleability of metal explain metallic bonding. All right. Similar to ionic. All right. So 91, metallic bond and ionic are similar. They both use positive negative attractions. The difference is metallic is a cation with electrons. Ionic is a cation and anion. 93. So 91 and 93 are the same thing. 96. All right, so real quick. All right, so here, 96. Melting point of beryllium is 1287. Lithium is 180. Large difference. Beryllium has much stronger metallic bonding and much stronger forces of attraction than lithium. They both use positive cation and negative electrons, but beryllium is actually +2 charge. Lithium is a +1. That factors in. That's more of an AP concept, but basically for the regents, what you need to know is if the melting point is way higher, it has stronger forces of attraction. So whatever's holding it together is much stronger. So that's the big difference there. Now back to 89 and 90, or no, 89 and 91. All right, really quick here. All right, so you got your positive cations here surrounded by a sea of electrons. This video is longer than I want it to, but that's okay. So you got all these negative electrons around it here, and they're moving around all over the place. So that's the attraction in the metallic bond is positive cations that are fixed. They're not moving, and the electrons are moving around like water. And describe malleability and ductile. So if you hit this row, for example, with a force, the entire row will shift. Now remember, this is just a snapshot. There's like trillions of these things, right? So I could fill this whole screen up, fill this whole room up. So if I hit this row and it shifts, so now this one is over here, all right? The crystal lattice here is still, it's just now there's like a dent. The structure is still intact, so now this cation is still going to be attracted to the electrons over on this side of the metal. So it just bends and moves because no matter how you push those cations, they're always attracted to the negative electrons flowing around it. My analogy of boats docked or anchored, right? If a boat's next to a dock and you push it hard enough, you can kind of slide it on the water, get it to move a little bit. It's the same concept. So it'll move and it doesn't completely break the crystal apart because of all the attraction and the fluidity of the electrons. The electrons are moving, so you can move the cations around. All right, I think that covers everything. I'm gonna stop the video now. So hopefully that was helpful. And how long did that take me? 23 minutes. That took way too long. But if you wanna get the answers, then I guess you'll watch it. All right, I'll talk to you guys soon.